Hello and welcome back to the channel where we are reviewing the Salvadori's textbook Structure in Architecture. So this video is about chapter 11 and that is all about the membranes. So let's talk about membrane action. The membrane is a sheet of material so thin that for all practical purposes it can only develop tension. A piece of cloth or a sheet of rubber is a good example of a membrane. So films are among the thinnest membranes we can build or blow the bubbles. And so film is also the smoothest surface connecting the points of the given boundary. So a minimum surface membrane represents the smallest possible surface area that can be created about a specific boundary. For every unique boundary, there will be one minimal space. It is akin to the funicular form of a cable. It is the shape that the soap film would take. So although membranes are two-dimensional resistant structures, they cannot develop applicable plate stresses, bending and shear, because its depth is very small in comparison with its span. Neither can it stand compression without buckling. Therefore, the load-bearing capacity of membranes is due exclusively to their tensile strength. So the sag of the membrane elements produces curvatures in two directions. The membrane may be considered as the intersection of two sets of cables. Each set carries a share of the load, and the total load carried by the membrane is the sum of the two sets of cable-supported loads. So a membrane is seen to be capable of cable action in two directions due to its curved shape, that is to the geometrical characteristics of its shape called curvature. It has now been shown that the two-dimensional resistant character of a membrane makes it also capable of a second load-carrying mechanism through the development of in-plane or tangential shears acting within the membrane surface. Please refer to the images in the textbook. You can see the cable actions in membrane, how the forces are directed. So also, you can see the shear development in plane of membrane as well as the geometrical twist. So the two pairs of equal shears on the opposite sides of any membrane element have directions that guarantee equilibrium in rotation. But a twisted membrane, the difference in slope between two equal shears on opposite sides produces an excess of upward forces. It is this excess that balances part of the load and gives the membrane its extra load carrying capacity by shearing action within its surface. So again, please take a look at the graphic here, which shows the portion of normal load carried by membrane shears. And you can see the upward forces and you can see the resultant force, how that acts within the membrane. So the difference is because of the twist, and out of plane component is generated. It is out of plane force that balances loads such as wind pressure acting against the surface. Furthermore, the equivalent principal compression force due to shears must be lower than the equivalent principal tension force, or the membrane surface will buckle since it cannot support compression. So membranes that do not tend to buckle are seen to carry normal loads without changing shape by three separate mechanisms: cable action due to curvature in one direction, cable action due to curvature at right angles to the first, and shear action due to twist. Any one of these actions vanishes if the corresponding curvature or the twist vanishes. And we are moving to the next subsection, and that's principal curvatures and principal membrane stresses. So the results obtained in the um, preceding subsection, which is the membrane action, indicate the two essential characteristics of that. A is membrane stresses, both tensile and shearing, are always developed within the membrane surface and never at right angles to it. And B, membrane action depends essentially on the geometrical characteristics of the membrane shape, that is, on its curvatures and its twist. So, in order to visualize the curvature of a surface, you must cut the surface with a plane perpendicular to it. So please take a look again at the graphical representation, how that is done. And you can see there are two principal directions, and also there are some diagonal directions as well. So the two perpendicular directions in which the curvatures become respectively maximum and minimum are called the principal directions of curvature of the membrane stress surface, and also a plane parallel to cylinder's axis will intersect along a straight line. A plane cut perpendicular to the cylinder's axis will be a semicircle and represents the maximum radius of curvature of the cylinder. Any other angle of cut will have a varying degree of curvature from 0 when parallel to the cylinder's axis to maximum when perpendicular. These minimum and maximum are, like we already mentioned, called the principal directions of curvature. So for an element of the cylinder with sides parallel to these directions, it's seen that the element has no twist. The horizontal slope remains horizontal as you move at right angles to it. But an element cut out of the cylinder with sides not parallel to the principal directions has twist. A surface may have twist in certain directions and no twist in others. So the only surface without twist in any direction is the sphere, since an element cut by any two pairs of parallel sides is identical to an element cut by any other two pairs of sides. And again, please refer to the images. You can see the cylindrical twist. You can see the principal curvature lines when there are more than one directions. So the tensile direct stress at a point of a membrane, just like the stresses in a plate, has different values in different directions. As the orientation of the tensile stress rotates around a point, the stress becomes maximum and minimum in two directions at right angle to each other, the directions of principal stress. So elements oriented in these directions do not develop shear. Shear instead becomes greatest at 45 degrees to the directions of principal stress. So the perpendicular directions of principal stress are those in which the membrane acts as two sets of cables at right angles. One set develops the maximum stress and the other set the minimum stress at each point. Shear stress develops between the cables in any other direction. So again, beautiful images here, cylindrical membrane dead load stress and internal pressure stress as well. And you can see the hoop tension that goes on the perimeter of the cylindrical membrane. So the analysis of cable action showed that the stresses developed in the cable are related to its span to sag ratio. Conversely, for a given allowable stress, the greater the sag, the greater is the load the cable can safely carry. Considering the cable action of a membrane along its principal stress directions, it is found that the direction with greater sag ratio um, carries more load than the direction with smaller sag ratio, smaller curvature. So in case of a sphere, the curvature is the same in all directions, and a spherical membrane under uniform pressure carries half of it by cable action in one direction and half of it by cable action at right angles to it. So please remember these equations. So in general, membranes must be stabilized because mostly their funicular shape for horizontal loads differ from that for vertical loads. And stabilization is obtained either by means of an inner skeleton or by pre-stressing produced by external forces or by internal pressure. So, and we are moving to the next subsection, and that's tents and balloons. So, for example, the Nomad's tent is a membrane capable of spanning tens of feet, provided its skins are properly supported by compressive struts and stabilized by tension guy ropes. The circus tent spans hundreds of feet using the same technology. The tent withstands the pressure of the wind, but even under ideal circumstances presents the drawback of moving under variable loads. Moreover, because of its lightweight, the tent vibrates or flutters under the action of a variable or even a steady wind. Tents are useful as temporary covers and acceptable as permanent roofs only if highly pre-stressed. So again, please take a look at the image here. You can see the circus tent, how that is um, developing the tensile structure. And I'm sure most of you have seen those every now and then. So large tents supported by complicated cable nets or vertical or inclined compression masts must have been used by Fry Otto to build temporary or permanent pavilions for fairs and other uses. So one of the largest to date covers that was built in 2015, and that covers more than 800,000 square feet, and that was um, that was the site of the 1972 Olympics in Munich, Germany. So it is supported by 9 masts up to 260 feet and has pre-stressing cables of up to 5,000 tons capacity. So it is interesting how it's interesting to see the variety of shapes here. So again, refer back to the images. You can see the portion of that cable net structure for that Olympic Stadium in Munich. And also you can see the single module that are connected together as constructed roof. So again, there is another example, and that is the Hajj terminal located in King Abdulaziz International Airport Terminal in Jeddah, Saudi Arabia. So it was constructed to shelter the millions of the faithful in the yearly Hajj pilgrimage. So it is constructed of 210 square modules. Each is 151 feet on a side. So it's interesting to observe this roof because it's a fabric membrane and the direction of stabilizing curvature is circumferential as opposed to downward curvature. One more structure here, Boston's Franklin Park Zoo Tropical Rainforest Pavilion. So that structure is supported by 3 large steel arches that support fabric panels. Take a look at that and you can find the pictures. So another example of a pre-stressed membrane with locked-in stresses is the umbrella. So the steel ribs pushed out and supported by the compressive struts connected to the stick tension the cloth and give it a curved shape suited for to resistant loads. So within limits, the membrane of an umbrella can take pressure from above and from below. The supporting steel skeleton reverses its stresses with the reversal of wind action, but the membrane is under tension in both cases. So take a look at that, and I'm sure you know how that works. So the Eskimo kayak is built by means of a membrane of seal skins tensioned by a skeleton of compressed longitudinal bars and circumferential rings pushed into it. A modern version of the kayak is built by means of a membrane or rubberized cloth stretched by an internal frame. So the interesting roof shapes of membranes pre-stressed by external forces are always saddle shapes. So for example, here you can see that's another pre-stressed membrane tent, and you can see it was constructed by architect engineer Fry Otto, um, and that is the simple hyperbolic paraboloid or saddle-shaped roof. So you can see there is a picture of that. So that's in the textbook. Please refer to the images. Um, membranes can be pre-stressed by internal pressure alone when they're completely enclosed volume or a number of separate volumes. Then they constitute pneumatic structures. Hot air balloons consist of an airbag open to the bottom where hot air from a burner enters and, being lighter than the surrounding cold air, makes the balloon rise. The airbag is reinforced by a series of ropes surrounding it. Membrane structures consisting of an enclosed volume are used, for example, in rubber rafts. The outer inflated ring is stiff enough to be used as a compression ring for the unstressed membrane forming the bottom of the raft. An inflatable airplane has been built on the same principle with inflated wings and an inflated fuselage divided into separate compartments. It was flown by using a light engine. Paraglider canopies and parachutes are also simple membrane structures. The long plastic balloons used at children's parties become so stiff when inflated that they can develop compression and bending action. The internal pressure locks into the cylindrical balloon tensile stresses in the circumferential and the longitudinal directions. The inflated cylinder supports compressive loads as a column up to the point where the compression due to the load equals the longitudinal tension due to the internal pressure. When the compression nears this value, the membrane buckles. Similarly, a balloon used as a horizontal, simply supported beam carries vertical loads up to the point where the compressive stresses in the upper fibers of the beam equal the tensile stresses produced by the internal pressure. The reader may easily prove that when you read this chapter further, that the compressive stress nears this value, the beam buckles at the top. And please take a look at the image here. And there is another image showing the Fuji Pavilion at Osaka World Fair in Japan. That was in 1970. This is a beautiful structure, consists of 16 air-filled fabric tubes bundled together in parallel rows. So you can see that, and that creates the internal pressure of the structure that can be increased or decreased in response to wind loading. Again, refer to all the images here because it is important to see that to understand. So inflated plastic mattresses similar to those that people use to lie on the beach or float on water have been used structurally as horizontal roofs, vertical walls, and inclined floors for theater floors. So all the pneumatic structures mentioned here so far are inflated, closed membranes. Some of the most interesting and impressive examples of pneumatic structures belong instead in the category of air-supported roofs and so-called balloon roofs or bubbles. So please refer to the images. You can see the Space Shuttle Museum pneumatic enclosure. So that's the flight deck of the Intrepid Museum in New York City. So that is quite interesting how that is formed. And there is another project, the Eden Project. So that's the contemporary development of the inflated structure is to use a rigid structure that supports a facade of air inflated pillows. The Eden Project by Grimshaw Architects in Cornwall, England was among the first projects of this type. So the skin pillows are made of ETFE plastic, a very durable yet translucent material. But built on the site of an abandoned quarry, the project is an environmental education center featuring biomes containing plants from several distinct climatic regions of the world. A noteworthy feature of this building is that because the skin dead load is so low, the structural frame has to do little more than support its own weight and withstand lateral wind forces. So the resulting total structure weight is so efficient that in total it weighs no more than the volume of air that it encloses, which is very interesting. So new material developments in the form of tough, thin fluoropolymers such as ETFE are spurring application in building skins. The thin films have been fabricated into air-inflated pillows, forming the envelope of some buildings, such as Eden Project, like we already mentioned, and the natatorium for the 2008 Beijing Summer Olympic Games, and that is known as the water cube. So given the material's lightweight, high strength, and excellent thermal properties, the success of these projects will undoubtedly spur on continued investigation and use of lightweight pillow membranes for facade applications. So also, what is important for this chapter that the technique invented by Dante Bini to build his Bini shells is an improvement on the NEF idea. A special type of sliding reinforcement is set on the detailed deflated balloon on which is also poured very fluid concrete. The inflation of the balloon lifts both the reinforcement and the concrete, which is kept in place by the helical steel springs sheathing the reinforcement and vibrated after inflation. Over 1,000 Beanie shells with spans up to 120 feet have been built and larger spans are technically feasible. So again, please take a look at the pictures, how that is created, and there are a few examples such as the Minneapolis Metrodome. So that's the air-supported stadium roof structure that consists of a skew grid of cables supporting a membrane. Also, what else is important here? Membrane roofs have been built not only of cloth and plastics, but of steel, aluminum, and reinforced concrete. Steel membranes, well adapted to carrying loads by tensile stresses, have been used to build stiff, permanent circular roofs in Austria, Russia, and other countries. Reinforced concrete may be so reinforced or pre-stressed as to take it suitable to the development of tensile stresses. The cable-supported roof may be considered a cable-supported membrane made up of metal sheet elements, and also the light metal structure have a tendency to flutter, while the heavier concrete membranes do not. So please remember those concepts. And that was it for chapter 11. Thank you so much for watching. I will see you in chapter 12.